How about now?
I can
There
hear
we
you.
go. I can hear you.
Okay. That's weird. So it gives me a window when I first open up and it asks me if I want to join the computer audio, but it also gives me an option to test my microphone. And I didn't want to just blatantly use whatever the computer audio is because I had this other device. So I thought I had to do that, but evidently that was the problem. So I just went back and it worked that time. So thank goodness everybody can hear me. That was worrying me for a little bit there. Still got about 2 minutes, so feel free to ask me questions if you have them. I was telling everybody that we have completed test 7, which was on 25 and 26. There's a test on 27 and 28 that's test 8. So I'm going to open that practice test up, and you guys have until Monday night to do it. So that'll just be another test under your belt. I've already got the practice test made, and I'm also going to make a practice final. I've actually got that just about made. I should open that tonight, or if worst case scenario, it should be ready by tomorrow morning. Your exam, it seems like maybe I'm just going to let you guys do your exam online, but you're going to have to all do it at the same time, basically. So it'll be during your lab time right after class on Tuesday. I think that's when your lab time is normally, right after class, right?
Yes, sir.
30 minutes or so.
Yeah, it's not a big deal. If you start 30, 45 minutes late, it's not a big deal. It's just a matter of I don't want anybody to be able to completely finish their test before someone else starts taking it for obvious reasons, but that should do it. And I'm just going to let you do it with the lockdown browser and the Respondus monitor. So just make sure you follow all the steps and all that good stuff. Show me your work environment and all that good stuff, and you should be good to go.
And then you said you have a practice test up tonight?
Yeah, I'll email everybody when it's actually up. I know I'll have the practice test. I've already got it made basically. So I know I have the practice test up tonight, and I've got the practice final made, but it's in a different course. So sometimes what happens is when I make it up in a different course and then I transfer it over here, it loses all the questions. So I don't know if that's going to happen again. Hopefully it won't, but it could.
Professor Younger,
Yes.
I have two questions.
Okay.
One being, is there any benefit for me to do the extra credit assignments on my lab and mastering, like the extra chapters, if I already have a good enough grade for the homework grade?
Not really. I'd say the only thing that might do you some good is perhaps some of the quantum mechanics or some of the relativity stuff. And even that really depends on what your branch of engineering or science that you're going into. Normally you would, this course is a 3-semester sequence. So normally you'd get a 3rd semester that would include nuclear physics, elementary particle physics, cosmology, quantum mechanics, relativity. You're not getting that. And normally we try to fit in some quantum mechanics at the end of the semester, but we weren't able to do that this time. So I would say it wouldn't hurt you if you had covered some relativity, which hopefully you got in 241. But if you didn't, that would be chapter 36, so that's worthwhile doing. Chapter 37 and 38 would be worthwhile doing, but it's not really worthwhile in the sense that it's going to help your grade. It's just worthwhile in the sense that it'll help you have a better understanding later, because a lot of times what happens is you end up getting relativity in a course where they already expect you to know some relativity. And they expect it because it's the 3rd semester of this course. So if you end up having to do something like that, that could be problematic. Same thing with quantum mechanics. So if you ever had to take solid state physics or material science stuff, sometimes you're going to have to require you to have some knowledge of quantum mechanics.
Okay, awesome. Thank you. And then one more question. Did you get my email regarding test 6?
Yes, I think I did. I remembered seeing it, but I'm trying to remind myself now. Let's see.
It was just about, like, I wasn't able to see the questions, and I didn't want to email you over Thanksgiving break because that's kind of a break.
That's what it was. Yeah, I remember saying that. I couldn't figure out what was wrong. It worked fine when I opened it. Let me check it again now. You said your test 6, when you opened it, it didn't show the questions, right?
Right.
Yeah,
And
so
it's locked now, so I can't really go back and do it.
Yeah, it shows all the questions right here. And let me try doing something else. Let me see if I can do. I'm gonna do a view of it just to see. And you said it's test 6.
Yeah, and I remember you saying something about practice test 6, just like don't do practice test 6, do like 7 or something, or 7 covering 6. So it was the
Gotcha.
same thing, practice test 6, that it showed nothing.
Yeah, that's weird. Yeah, I'm looking at it right now. And it seems to be working fine for me. I'll try to. I mean, the problem is I really want you to have experience taking this test, but I don't want to overburden you with it. So what I'll try to do is open it back up in hopes to see what's going to happen. But it looks like it's only 11 questions long. It looks like it's got the right number of points and everything. So I don't know what's happened. Did anybody take test 6? Test
So
6 was on. Go ahead.
when I tried to take test 6, I had the same issue. I sent you a message on Canvas about it. But so it's
Yeah.
showing test 5 and test 6 are both on chapters 23 and 24.
Yeah, that's what I just noticed. I think that's the problem.
So
Yeah, it
like
also didn't work for me.
Okay, cool.
You had extended test 5 after like people hadn't taken it.
Gotcha.
I was one of those people, and so like I took test 5 when you extended the due date, and then test 6 was like 2 or 3 days after that, and so I opened it right afterwards. I was like, oh, it's the same chapters, I might as well take it, and it had no questions on it, and when I hit submit, it gave me a 0 out of 100.
Gotcha.
So,
yeah, don't worry about test 6 at all. I see now. Yeah, and I think I discovered that last week that it was the same chapters. So yeah, test 5 is plenty good. What I'll do is I'll go in and I'll look at everybody's grade, and if anybody has a higher score on test 6, which I don't think will happen, than they have on test 5, then I'll copy that score into test 5, and only test 5 will count.
I did have a question. So you sent a message out, I think sometime last week, about like the chapters that like are due for like homework and stuff. You said it goes up to 31. Have we done 31 yet, like in class?
No, that was supposed to be tonight and next time. But it's really a cursory covering of it. I'll pretty much tell you what you got to know. There's an extra term that Maxwell decided had to be added to Ampere's law, and I'll do that derivation. But really, to be honest with you, without that particular term, you can't get the wave equation. And the wave equation has a very specific solution. So it has sort of like when you did chapter 14 and 15 and 241. Remember how they give you like x is t is equal to 32.8 centimeters times cosine of 8.64 t minus 3 pi or something like that. And you can look at that actual solution, and from that figure out what omega is, figure out what frequency is, what the period is, what the amplitude is. That's the kind of stuff we're going to be doing for 31. So it shouldn't be too terribly hard. You also have stuff like using what I call the kindergartner's wave equation, which is velocity equals frequency times wavelength. So you need to know the electromagnetic spectrum, which is I have a mnemonic that I use for that. It's great excess undermines various industries' Marxism rules. And I'll type it up for you guys right now. I'm doing that. Hold on.
I also had a question regarding the final.
Okay. Hold on a second with that. So that's my mnemonic I use for the electromagnetic spectrum. And what that is gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, and radio waves. All of those are what we call EM radiation. And what that means is they all travel at the speed of light. So I can ask you a question like, what's the wavelength of the carrier wave for FM 93.7? And velocity equals frequency times wavelength, and it feels like you only have one of those pieces of information. Like 93.7 might mean something, and it does. It means 93.7 megahertz. So you would put 93.7 times 10 to the 6 for the wavelength. But the other part that you know is because it's electromagnetic radiation, you know the speed is 3.00 times 10 to the 8th meters per second. So you can solve for the frequency. Similarly, when you do the V equals F times lambda for AM, I could say, for instance, AM 850. Well, that means kilohertz. So you say 850 times 10 to the third is the frequency of the carrier wave for AM 850, and then you can solve for the wavelength. I might have said wavelength and frequency backwards on that previous example, so just check me if I did. Go ahead with your question now about the final.
So is the final going to be structured like last test or like the first test? Because last test, the weighting of the questions was like it was all over the place. Because like the
Yeah,
first,
some of them were big points and some of them were small points.
yeah, and
Like,
those for me, those the ones that were worth big points, I was not good at because like they weren't similar to the ones on the practice tests, which I was
yeah.
under the understanding that if I was good at the practice tests, I'd be good at the test, and
Yeah,
that was not
and
the case.
so they'll definitely be more like the previous test, not that last one. Not only that, I still owe you guys some credit on that because I screwed up part of the test. All of that will be fixed no later than Friday. I hope it'll be fixed before then, so you will know when you go to take your final what your grade is going into it. So that the only thing you might not know, and that depends on your lab instructor, is regarding your labs. But normally she gets her labs in well before the week of the exam, so you might even know those Friday. But yeah, the only time I'll on this final that I'm likely to count things as extra points is if there's maybe one where I actually ask you to actually derive using Gauss's law or derive using Ampere's law. That one might count a little bit more, or in general concept questions. If I give you a concept question, that might count a little bit less. But my intent is to do somewhere around 20, 25 questions, and ideally I'd like them all to have the same value so that I can have 3 or 4, maybe 5 problems that I consider a little bit tough, but because they're a little bit tough and still count the same, you can make up for it by knowing how to do the what we call the chucker problems, which are, simple stuff like electromotive force is equal to BLV for any conductor of length L in a magnetic field B, moving with velocity V perpendicular to the magnetic field. So that's one where it's just a blatant formula. You just plug it in and do like that. That's what most of the questions should be. And then you'll have a couple where you're actually going to have to do some work, derivation or something. Those generally I try to keep them all have about the same points. Okay.
Professor,
Yes.
so I just wanted to double check. So I have a couple late assignments that I plan on getting done. I just want to know when the very last date to turn those in is.
So generally speaking, if it's something that you were turning into me, which it's not because you're not a lab, the homeworks are going to be late based on and they're going to have points deducted based on the rule that I set up for grading within my lab and mastering.
Yeah. I was just wondering, so I just need to get the ones done before the exam, basically.
Yeah, I think I've got a deadline of like the 4th. So it's like either
Okay.
Sunday or Monday.
Yeah, that's no
So it's
problem. I
either
just wanted to
3rd or
double check that.
Yeah, I would
Okay.
try that. And to be honest with you, if you're missing a lot of homeworks, I would say it's probably more important that you focus on being able to do really well in the final, because doing well in the final can erase a lot of misdeeds in terms of missing homeworks and stuff. So yeah, I'd worry more about that rather than catching up, because the homeworks are really just for you to do better on the tests.
Got it. All right. Thanks for the advice.
No problem.
And the lowest couple homeworks and tests get dropped, right?
Yeah, I think I said I dropped the 2 lowest, but at least I know I always drop at least the 1 lowest, and then every time I add an extra credit, I drop another one. So, and I know I've added at least 2 extra credits.
Professor Younger, I also have 2 more questions.
Yes,
I'm
go
so
for it,
sorry.
Anna.
Everyone's like bombarding you right now.
No problem.
So, you told us we're gonna get our actual grade on Friday in the lecture class, correct?
Yeah, you should get it definitely by then, but hopefully before then.
And then as for my final, were you able to figure out when I would be able to take that?
Yes, and you sent me, I think you sent me a couple of emails over the break. I mean, over the weekend and the break.
Yeah.
I will probably have it ready as early as I could possibly have it ready tomorrow, but I'll definitely have it ready Thursday.
Okay, so I can take it Thursday.
And in fact, you don't even have to go to the testing center because I decided to let everybody take it with the Respondus lockdown browser. So,
Okay, so is there are we taking it all on Thursday, or do you want to take it that day next week?
aren't you one of the people that'll be out of the country or out of?
Yeah, but I'll still have like internet access to get
So
it
you could
done.
actually take it there. Well, if you can take it
Yeah.
then, that would be better for me.
Okay.
Yeah, that way I wouldn't have to make, because otherwise I have to make one for you and then a slightly different one for
Yeah,
everybody else.
that works. I can take it the day of as long as it's on Respondus.
Yeah, it'll be a Respondus
Yeah.
lockdown browser. So
All
no
right,
problem.
thanks, Professor Younger. Appreciate
You're
you.
welcome. Anybody else? Okay, so when we last talked, we were in chapter 28 and I was working up to AC circuits, and specifically I was working up to AC circuits with L, R, and C. In other words, with inductors, resistors, and capacitors in it. And I went through the part where they have a resistor in section 30-7-1, and then they had an inductor in section 30-7-2, and then they had a capacitor. And in those derivations, I was able to show you that basically Eli the Iceman is the rule. And Eli the Iceman specifically means the electromotive force leads the current in a inductor. Notice that's ELI, electromotive force E, leads the current I in an inductor L. So that's what we get Eli from. And then Iceman is the current leads the EMF in a capacitor. And that sets us up to do a phasor diagram. And that also derived a formula for the actual impedance and reactance for the circuit. So the reactance is sort of like something like resistance, but it's for a particular item. So when you talk about reactance, you're thinking, okay, there's an Ohm's law sort of scenario where V equals I times, normally R would be the case in Ohm's law for a resistor, but in this case, it's V equals I times X, where X is either XL for the inductor or XC for the capacitor. And you have to know those quantities as well. So I did all that derivation works. Now we're going to just apply it to a particular circuit, and I'll have to show you that with regards to a phasor diagram. So I've got the document open right now, and I'm going to go ahead and share it with everybody, and we'll walk you through this particular problem. So hopefully we'll be able to get all this to work. So give that a second to come up. I'm going to write across the top that we have Eli the Iceman, so y'all will know what I'm talking about. So Eli the Ice Man. Actually, I'll just make a lowercase m. Okay, and this means EMF leads current in an inductor. L, and current leads EMF in a capacitor. C, okay? And what we know is XL is equal to omega L, and XC is equal to 1 over omega C. And remember, of course, omega is equal to 2 pi times F. So hopefully that'll help you a little bit. The main thing is the units of X are ohms, okay? And then the other thing, which we'll see in a second, is the reactance. These are the reactants, but it's the impedance. So there's also something called impedance. and that's a quantity Z, and we'll work that out. So we're going to use all this stuff, but what I'm going to do is I'm going to give you an example circuit. So let's imagine we have an AC source down here that looks like that, and in it is a wire that comes up, and that wire is going to run into a capacitor, and then that's going to run into a resistor, say, and then that's going to run into an inductor. Okay, this C, I'm going to say is, let's try 24.0 microfarads. This R is, let's say, 50.0 ohms. And this inductor L, let's say that is 60.0 millihenries. And let's say our voltage is 50 volts and that it has a frequency of 500 hertz. And I'm going to put a decimal after that to make it seem like I have 3 sig figs. In fact, I'm going to go ahead and erase that 50 and call it 50.0. So that's 50.0 volts. Okay, so it looks like everything has 3 sig figs. What we want to do is, this is the problem. And I'm going to draw a line like this. Okay, and what I want to know is what is IRMS? Okay, so we're wanting to know the root mean square current. This, by the way, this 50 is VRMS. I didn't actually say that, but that should be what you assume unless we tell you otherwise. So if I tell you you have an AC source and I give you a voltage, but I don't tell you explicitly what it is, you should assume it's a RMS voltage. B, we're wanting to know what are the voltmeter readings. So VRMS equals question mark for R, L, and C. And then for part C, what we want to know is the phase angle. Which a lot of this wording should sound completely foreign to you unless you've actually worked with AC circuits before. So what is the phase angle phi? And then finally, D, what is the power dissipated? Okay, so we're going to try to figure out all those questions. It shouldn't be too terribly hard. Here's where our solution comes into play. What I'm going to do is make use of the phasor diagrams, because in principle, what you would do with this kind of circuit is you create a differential equation, and then you take some initial conditions down and you solve the differential equation, and that's quite nasty. It can get really ugly. And then your initial conditions, you implement all that, and all the stuff could be, it works out, and it's not too terribly hard, but it's a lot easier doing what I'm saying right here. So what I'm going to do is show you a phasor diagram, and I'm going to do it right here in red. And hopefully that will help you guys better understand how to deal with the AC circuit. Your book has some problems in the back of it. I think 81's one of them. Might be 81 or 89, something like that. Oh, no, it's 89, 91, and 96, where it allows you to examine other AC circuits other than these that are all in series. So what, for instance, would happen if you had an AC source in parallel with a resistor that's in parallel with a capacitor that's in parallel with an inductor? All that kind of stuff is what we're looking at. So with a phasor diagram, what you do is you draw a coordinate system And this part is kind of odd, but I'll tell you what's really going on here is you have an x-axis that is like what we can actually measure. That's real stuff. And then there's a y-axis that's actually the imaginary axis. Okay, so when I say something like Eli, what I'm saying is the voltage is 90 degrees ahead of the current. And what we see here is the current is going to be basically the same for all of these, because conservation of charge dictates that once, 3 coulombs of charge leaves the left hand side of that power supply, all of the circuit parts are going to get 3 coulombs of charge. So there's no ifs, ands, or buts about it. Now the voltages can do quite a bit of different stuff. So what I'm going to start off drawing here is I'm going to draw a current over here, and that's going to be the current that's coming from the AC source. And all we know is that it is I is equal to I0 times, basically you can take some kind of cosine function or whatever you want to do. Doesn't really matter too much. But if you look back at the previous sections where we did 30-7-1, 30-7-2, 30-7-3, and that sort of stuff, that was what we were looking at. So we'd say I0 is equal to cosine, or I0 times cosine omega t is what the current is. Okay. Now, what we learned when we examined the resistor is that the voltage is actually exactly in phase. The voltage across the capacitor, or across the resistor, is exactly in phase with the voltage, with the current through the resistor. So this is VC, and that's going to be equal to, basically you can say V0 sine omega t, and you see that it's immediately in phase. But what you got to realize is V0 is just I0 times R, and then times sine omega t. So that's what we mean when we're talking about the current and resistance are in, or excuse me, the current and the voltage are in phase for a resistor. And I don't know why I wrote capacitor there, but I clearly did. So let's do this. That's the voltage across the resistor. And make sure that R looks enough like an R. So that's good there. Okay. So that's what's going on with the resistor. That's what we learned in section 30-7-1. 30-7-2, we learned that the inductor was actually the L part, and the voltage is actually ahead of the current in that one by 90 degrees. So what we see here is we have the voltage for the inductor, V sub L, is actually going to be equal to I0 times X sub L. And in this case, it's times the sine of omega t plus pi over 2. That plus pi over 2 is what we discovered, and that's what told us that it was ahead by 90 degrees. And then back here, and I'm drawing, by drawing these arrows certain lengths, I'm making certain assumptions. Like, for instance, I'm thinking that the reactance for the inductance is bigger than the reactance for the capacitor. That's why that VL vector is so much longer than the VC vector. The VC vector is going to be I0 times XC times the sine again, but this time it's omega t minus pi over 2. So that's where we get ice, and the other one's where we get Eli. So just for the record, we'll say Eli, and just for the record, we'll say ice, like that. Okay. Now, after a certain amount of time, what's going to happen is, let's do another color here so I don't have to crowd up the joint. After a time t, oops, that is not the right color. After a time t, this theta will be equal to omega t, and this will be VC, and then 90 degrees ahead of that will be VL, and then 90 degrees behind that will be VC. So if you wanted to at any particular time, if you wanted to find out exactly what the voltage across the capacitor is, you draw a vertical line from the end of that little VC green vector and find out how long the X component is. Notice that's in the positive direction. Then you draw a vertical line from the VL. Notice that that casts a shadow on the negative X-axis. So that would be a negative voltage across the inductor. And then you draw another vertical line from the VC up to the X-axis, which again is positive, and that would be the voltage across the capacitor at any point in time. And that's how you could get them at any point in time. What we're going to calculate, though, is the root mean square voltage across each one. So that's if you actually connected, say, a multimeter to the actual device, it would read what the RMS is, because each of these are going through a cycle thing. But oddly enough, the cycle thing for the inductor has the voltage going up and down 90 degrees ahead of the current, and the voltage for the capacitor has the voltage going up and down like the current, but again behind the current, and the resistor has the voltage going up and down in phase with the current. So that's really what's going on here. And from that, I think you can see, I'm going to do yet another color. Let's do this fancy pink. So you can see that the X component really is, at least when it's when the thing was horizontal, the X component is just the length of VC. But the result of all this is this little pink vector right here. And that little pink vector is the voltage, in some sense, of the circuit. And what this angle is called the phase angle. And what you can see is that we're going to say a voltage. Whoa. We're going to say there exists a voltage across the circuit, and that's represented by this little guy. And that's equal to I times Z, where Z is the impedance that I talked about here. And that's going to be I times the square root of, now we're going to just take R squared plus XL minus XC squared. So this little component over here, the one that's perpendicular to the dark green vector, that one has a length of XL minus XC, and the horizontal one has a length of just R. So you're using the Pythagorean theorem. So that's how all that works. That's how that phase works. You can see, for instance, that the inverse tangent of phi is equal to opposite over adjacent, which is, of course, opposite is XL minus XC, and then adjacent is just R. So that works. But you could also say, and I shouldn't have said cosine inverse, that's just our tangent inverse, that should just be tangent. There you go. Similarly, you could also say, I'm going to use a different color now. I could also say that cosine phi is actually adjacent over hypotenuse, and that would be basically R over square root R squared plus XL minus XC quantity squared, like that. Okay, that comes in handy, as we'll see, because that's related to the power. It's basically called the convert, or the power factor, the cosine is. So when I do this, what I first need to do is I need to go through and figure out what the net impedance is, so that I can then use that in each of these expressions and make some sense of it. So first off, I'm going to say XL. Well, actually, I did decide I was going to do this in blue, so let me go back and do it in blue. So XL is equal to omega.
We cannot see the bottom of the page.
Oh, you can't? Okay. Can you now? Yeah,
Yes.
it's just, okay, there you go. Sorry about it being so small. And these formulas are all in your book, of course, too, but still, you should be able to see that. So that's XL minus XC in there. We're going to do it again when we actually do the calculation, so don't worry too much about that. But what we're going to do here is we're going to say 2 times pi times 500 hertz. Okay. And then times XL or excuse me, times L. And what we said was L was equal to 60 times 10 to the negative 3 henries. Okay. So when I compute that, I'm going to get 2 times 3.14159 times 500 times 60 e to the negative 3. And that gives me 188.5, 188. And since that's 5, I need to carry 2 digits that are not correct. So I'm going to say 4, 9, like that. And that's ohms. So that's the reactance. That's called the inductive reactance. There's also an XC, and the XC is 1 divided by 2 times pi times 500 hertz times C, which we said was 24 microfarads. So I'm going to say 24.0 times 10 to the negative 6. Whoa, that did not turn out well. So this is going to be 24.0 times 10 to the negative 6 farads. And what I'll get is 1 divided by 2 times 3.14159 times 500 times 24 e to the negative 6, close parentheses. And that gives me 13.2. So I'll call that 13.26. One extra sig fig there. And that's ohms as well. This was farads. And of course, we already know the resistance. So now I can say that Z is equal to the square root of R squared. And R, of course, is 50. So I'm going to say 50.0. I'm going to leave the units off here just for room. Now I've got to do XL minus XC. And this is going to be 188.49 minus 13.26. That's all going to be squared. And then I got to take the square root of all that. So I'm going to get 50 squared plus 188.49 minus 13.26, close parentheses, square that. That gives me the square root of 33,206, which is 2 extra sig figs more than I should have. So now I'm going to take the square root of that. And that gives me 182.2. So this is 182.2 ohms, and that's called our impedance. Okay. Now, why do we need that? Well, the voltage for part A, the voltage across the resistance is just, if you use it this way, the RMS voltage is just the RMS current times R. So we already know what the R is, and the RMS current, I'll put it down here, is 50. Oh, excuse me. I got to first figure out something else. So I know that the voltage of the device is what determines what my current is. So for part A, oops, I just erased everything. That was awesome. For part A, and let me figure out what I just erased here. I just erased a bunch of stuff that wasn't supposed to happen. There you go. So V RMS for the circuit is equal to I RMS for the circuit times Z. So that means I RMS is just equal to V RMS, which is 50.0 volts, over Z, which is 182.2 ohms. So if I do That gives me 0.2744 amps. And that's one extra sig fig that I'm supposed to use. So that's basically 274 milliamps. So IRMS is equal to about 274.4 milliamps. So that's the answer to part A. Anybody have any questions on that part? So the second part, they want to know what's the RMS for each of the individual components. And that's the beauty of using RMS is you can put in RMS and out pops RMS. So I'm going to go to the next page and say part B. So V R RMS is equal to I RMS times R. So in this case, I get two, actually I should keep it as, I should keep it as actual amps. So I'll say 0.274, not that, 4 amps times the R, which we said was 50.0 ohms. So I'm going to say times 50, and that should give me 13.72. Again, carrying one extra sig fig, and that's VRMS. Actually, I put that so close, it wasn't easy to see that that was a 1 next to it. Okay, now we do the same thing for V, let's say VC. RMS is just equal to IRMS times XC. So this is again 0.2744 amps times, in this case, I think we had XC was 13.26. So times 13.26 ohms. So I want to multiply 0.2744 times 13.26. And that gives me 3.638 volts. And this, of course, is volts across the capacitor RMS value. So I will box this off, and that's another part for part B. Anybody have any questions on that so far? Okay, now I have V sub L, which is the voltage across the inductor RMS value, is equal to IRMS times XL, which equals 0.2744 amps times, I think this one was 188.49. And that's ohms as well. So I'm going to say this times 188.49, and this gives me 51.72. And that's volts, and that's equal to VLRMS. Now, one of the main reasons we're calculating that is I want you to see that, in fact, if you add these three voltages, you get 51.7 plus 3.63. That's about what, 54, 55.3. And then another 13, that's about 68. Notice that's way higher than the RMS voltage for the circuit. The RMS voltage for the circuit is just 50 volts. So that's completely normal, though, because the reason that they're saying that is that's the average over a whole cycle. In other words, they take the voltage over an entire cycle and they square it. Then they integrate that over one whole cycle, in other words, one whole period, and then they take the square root of that, and that's the root mean square. but you wouldn't find at any point in time a voltage across the resistance being 13, a voltage across the capacitance being 3.6, and a voltage across the inductor being 51. That's never going to happen all at the same time. That's why you don't have to worry about it not adding up. Does that make sense to everyone? All right. So now we're going to do part C, which is the phase angle. So we'll use, since I wrote the cosine in such a way that it wasn't easy to see, I'm going to use the cosine is equal to R over, that's adjacent over hypotenuse. So that's just R over Z, which is equal to 50.0 ohms, right? Yeah, 50.0 ohms divided by, we got, what was it? 182.2 ohms was the net impedance. So 182.2 ohms. So that says phi is equal to the inverse cosine of 50.0 over 182.2. So the phase angle is going to turn out to be 50 divided by 182.2. And now I'm going to take the inverse cosine of that. And that's the inverse cosine of 0.2744, by the way. So I end up getting about 74.07 degrees, and that's one extra sig fig. So that's what the phase angle is. Okay, so that's your answer for part C. Now, remember I said this is the cosine inverse of 0.2744. Okay, that comes in handy specifically because it turns out when you actually try to do the power, there's several things you can use. But power is P equals IV. That's one scenario. Power is I squared R. It's also V squared over R. All sorts of crazy stuff. And all of those mean different things when you're actually trying to do it in AC. So what I'm going to do is for part D, I'm going to say that the average power P bar is equal to IRMS squared times Z times cosine phi. It's also, of course, IRMS times VRMS times cosine phi. But if I were to try to use I0 or V0 on any of those, I'd have random factors of 2, the square root of 2, and stuff like that. That's why I almost always do all my work in RMS. So what I'm now going to do is go ahead and calculate what this power is. So the average power dissipated, and by the way, I should point out, even though I did last time, the capacitance and the inductance, since they're out of phase, you basically have V being a maximum when I is 0 and I being a maximum when V is 0. So you're never going to get any power dissipated by the capacitance or the inductance, but you will get it for the resistance, and that's what we're calculating here. So what we're going to calculate here is the average power, which we're going to say is IRMS times VRMS times the cosine of phi. And of course, we know that IRMS is 0.2774, or excuse me, 2744. And I think that's what it was, 2744. Yes. 2744. And that's amps times VRMS, which is 50.0 volts, times 0.2744 was the cosine of phi, which oddly enough happens to be the same thing as the current, but that's just a freak of nature. So 0.2744 times 50 times 0.2744 gives me 3.765 or 3.76. And then since it's not exactly 5, it's 47. I want to make sure I include both of those. And that's watts. So the actual power dissipated in this case is 3.76 watts, basically. Any questions on that? So that's it. That's how you treat a AC circuit. Your book does talk about resonance. What I will tell you is that if you look at the formula, so regarding resonance, let's go ahead and do this, break this off. Notice your Z, whoa, Nelly. Notice that your Z, the impedance, is equal to the square root of R squared plus XL minus XC squared. And that implies I is, I don't know why I subscripted that. I is a maxima when when Z is minima or minimum. So XL equals XC implies Z is a minimum. Oops. Oh, I really want to put an A there. Ooh, I can't believe I did that earlier too. So that's Z is a minimum, and that implies I is a max. So that's what resonance is about. And you can do that, for instance, if you have resonance, that means you get the most output from the circuit. And that can happen by you making sure XL and XC are equal. If you do that, that's a very specific frequency at which that happens at. And if you set up your circuit so that like you're tuning into a particular radio station, that radio station will have that frequency that makes XL equal to XC. And then it will be, it will hit an amplifier, and then the amplifier can amplify that signal. I'm not going to require you to do anything with resonance in AC circuits, nor am I going to require you to do impedance, nor am I going to require you to do three-phase or AC. But those three things are topics you should probably read over, and I tried to remove them from the question banks for the practice final. But they might pop up in there, but I will make sure they're not in the final. Okay. Any questions on that? All right. So that basically finishes off chapter 30. What I want to do now is go into chapter 31 and specifically a shortened version of chapter 31. So first off, what we have is Ampere's law, which says the closed integral of B dot dl is equal to mu 0 I enclosed. Y'all all recall that, hopefully. And what I want you to think about is imagine this wire coming in like this, and then the wire runs into, say, a capacitor. And let's say the capacitor is right here like this. And then the wire leaves like that. Okay. Now, if you were, for instance, assuming some kind of currents flowing through here and here, then you could take an Amperian loop like we've been doing, and you would actually have to do it this way, down and in front of the wire. And then back here behind the wire, it's going to go up like that. That's your Amperian loop. But the nature of this closed integral of B dot dl is that it came from a different integral, and that integral was an integral of a curl. It was the curl of B over a surface, and that surface was bound by this curve. So when I try to apply the left-hand side of B dot dl, the left-hand side of the integral of B dot dl is supposed to be applied to any surface that's bound by that curve. So one particular surface, for instance, might be this guy. which is all well and good, but what if instead the surface is this guy? Notice how it goes right in between those two plates. And if it goes between those plates, we know that in fact, no actual charges jump from the left plate to the right plate. In fact, if it did, that would be the capacitor failing. We sort of get the equivalent when we put in AC voltage and current through there, but it's literally no current going through it. So in fact, this particular surface implies I enclosed is equal to 0. So if we use that as our surface, we would get that there's no magnetic field going through the middle of that little loop. And that's what Maxwell saw and said, well, I need to fix that. Something's got to happen. So it's one of those things where, just like we did before, remember when I derived the energy stored in a electric field, and then I did later the energy stored in a magnetic field. For the electric field, I got epsilon 1/2 epsilon 0 E squared. And then for the magnetic field, I got 1/2 times mu 0 times the magnetic field squared. Well, I did those in the case of the electric field for a capacitor, but it turned out to give me the right answer that was generally right, even though I did it for a capacitor. And the same thing happened when I did it for a solenoid on the magnetic field. Well, it turns out you can do the same thing here, is you can think about what exactly has units like a current when you're talking about a capacitor. So you can actually say something along the lines of, I need something that looks like a current that I can follow after a mu 0. And in doing so, I want that quantity to come out like a current. And in fact, they called it the displacement current. So that's what I'm going to do now. I'm going to say, we know C equals QV. Okay. And for a capacitor, of course, we know that that implies that the Q, excuse me, I said Q equals CV. Let me erase that. It's actually C, whoa, no. It's actually C equals Q over V. And from that, we can say Q is equal to CV. And C, we know for a parallel plate capacitor, is epsilon 0 A over D, where A is the area of the plate and D is the separation between them. And then V we know as the electric field times the distance. So that's just E times D. So what you can see in doing that is ultimately you just get that this is epsilon 0 A times E. So we know that I is in general dq over dt. So we might think that I would be epsilon 0 d by dt of A times E. And if we think what A times E is, we might reach the conclusion that maybe this is pointing to electric flux, and that's exactly what it is. So we're going to say epsilon 0 times d phi E. Notice I subscripted it with a E instead of a B, and that should be our displacement current. And again, this name, displacement current, is partly a descriptive term, but it's a descriptive term about a current that was based on an idea or a theory that didn't pan out. So it doesn't have any really good physical meaning for us anymore. It's just historically what the name is. So don't try to find out exactly what they mean by displacement here, because it's not going to be fruitful for you. So with that in mind, what we have to do is say displacement current is epsilon 0 d phi E over dt. So now we can say Ampere's law with Maxwell's correction is the closed integral of b dot dl is equal to mu 0 times I enclosed plus, now this time it's going to be epsilon 0 d phi over dt, or since I wrote that so close to the edge, it's mu 0 I enclosed plus mu 0 epsilon 0 d phi e over dt. And that's the actual correct Maxwell's or Ampere's equation. Any questions on that? So now I can restate Maxwell's equations. And your book actually does a derivation of this in appendix, I think it's appendix F. But basically what we had was Gauss's law, which says the closed integral of E dot dA is equal to Q enclosed over epsilon naught. Well, it turns out if you do the exact same thing to the magnetic field, you just get 0. And both of these are called Gauss's law. This one on the right is for the magnetic field, but that also shows there's no magnetic monopoles. Okay, meaning we don't have any isolated north poles or south poles that exist. Therefore, you can't have something on the right-hand side that's like a source of magnetic field. So that's why that portion of Maxwell's equation has a 0 on it. That we'll call this 1, we'll call this 2. Now we also have the other equation, which was Faraday's law, and we can write it a little differently, but Faraday's law we can say is the closed integral of E dot dl is equal to, let's say, E, which is negative n d phi b over dt. In other words, E equals negative n d phi b over dt was the Faraday's law that we're familiar with. But I just wanted you to know that in principle that E is really an integral of E dot dl because that's the definition of voltage. So we get a similar expression for the other one, and this will be equation 4. And what that is the closed integral of B dot dl is equal to mu 0 I enclosed plus mu 0 epsilon 0 d phi e over dt. Now, all we really need to do to go from these Maxwell's equations in integral form to Maxwell's equation in differential form is we need to apply some integral theorems, some vector calculus theorems. One of them is called Gauss's law. So Gauss's law, or you might say Gauss's theorem, which basically says that the integral of E dot dA is actually equal to, what we're doing here is we're calculating the flux of the electric field outside of a surface that's closed. And what we find out is that's got to be equal to how much stuff is leaving it. And the word for leaving is divergence. So this is actually equal to the integral of del dot E dA. Okay, so that's the divergence of the electric field. And all this Gauss's theorem says is, hey, if you're claiming a bunch of stuff is leaving a volume, then we better be able to calculate exactly what's leaving the volume by calculating how much is leaving through the surface. So the left-hand side is us integrating over the surface to see how much is leaving, and the right-hand side is us telling you how much is leaving. So that's one of the equations. So from that alone, we can see that ultimately we're going to get the integral of the divergence of E dA. Actually, that's supposed to be a volume. Sorry about that. And actually, I'll do it this way. Okay. And this guy right here is also supposed to be a volume. Whoa, that went badly. Okay, so that's what the left-hand side of Gauss's law is. But now I want everything to be in terms of a integral over a volume. So I'm going to write 1 over epsilon 0 here, and I'm going to change the Q enclosed to the integral of rho dV. And now you can sort of adjust the rho so that it only has a non-zero value within the volume of the charge, in which case you could just set the two integrands equal to each other, and we get del dot E is equal to rho over epsilon naught. And that is Gauss's law in differential form. And you can, as you might imagine, you can also get del dot B. Oops, I should probably write it in black. You can get del dot B is equal to 0 the same way. Now, the other part is something called Stokes' theorem. And it's sort of like Gauss's theorem, but what it says is if you want to calculate the curl, which is how much something sort of swirls around on a surface. So if you want to calculate del cross E dotted with dA, then we can either calculate it by calculating the actual curl on the surface, or we can just take a contour around that surface and do a line integral around there to get a feel for how much of it's in sync with the circuit. So you get that this is actually equal to the integral of E dot dL. That's what Stokes' theorem says. So when you look at, for instance, Ampere's law, you'd say the closed integral of E dot dL is actually going to be equal to the integral of del cross E dotted with dA. And let's ignore the N right now. Just know the N is what you put in when you've got multiple circuits or whatever. But the main thing is you're going to have on the right-hand side, you're going to have d phi over dt, which we can convert to partial with respect to t of the integral of B dot dA. Yes, because it was a magnetic field. So now you're seeing that we, in fact, have two integrals, del cross E dotted with dA and B dotted with dA. So this tells you that, in fact, del cross E, actually, I should write it in black to be consistent with what I was doing before. So I now get del cross E is equal to, and there was a negative, which I dropped, by the way, is equal to negative partial of B with respect to T. And you can also see similarly that del cross B is equal to, looking back again, in this case, we're going to get mu 0 times j hat, because I is equal to the integral of j dot dA. Okay, so that's where the j came from, plus mu 0 epsilon 0 partial of E with respect to T. And that's our last two Maxwell's equations in differential form. So if you were taking a more advanced course, you'd have nothing but differential equations that you're working with, at least initially, and you would solve these differential equations. As you can see, these first two have no time dependence whatsoever. So if you're looking for how it's going to evolve in time, you really got to isolate yourself to looking at Ampere's and Faraday's law. Whereas if you want to talk about sources like J or rho, then you're going to use the divergence over here, and you're also going to use the J for Ampere's law as well. So that's the actual equations. It turns out you can put all those together, and when you do so, you get something like this, and I'll just say putting these together. And your book actually does this with a really ingenious derivation, but you can put them together in special ways. I have a way on my YouTube channel that you can check out. Your book does a different way. All of them is really wonderful, but basically what you end up getting is the second partial of E with respect to x squared. And in fact, it's something bigger than that. It's actually the second partial of E with respect to x squared plus the second partial of E with respect to y squared plus the second partial of E with respect to c squared, which is a operation that we define in vector calculus, but you're not necessarily required to know that. So we'll just treat it as one-dimensional. And the nature of a wave equation is always a second derivative in space and then a second derivative in time. Now, these two have to have the same units, and you can see it's E per x squared or E per meter squared, and on the right it's E per time squared. So if I were to multiply the bottom of the right-hand side by a velocity, then I would actually get meters per second times a second in the bottom, and the second would cancel out and that'd make it meters, but I need it squared. So I need 1 over the velocity squared. Okay. Well, when this was done by Maxwell, something really cool happened. He got something along the lines, and I'll put it this way instead, second partial of t with respect to time. Yeah, I'll do it this way. Actually, no, I don't want to do it that way. I'll say the second partial of E with respect to space is equal to mu 0 epsilon 0 second partial of E with respect to time squared. And guess what? If you take 1 over the square root of mu 0 epsilon 0, you'll get 299,792,458 meters per second. So when Maxwell put these equations together, he got one like this for the magnetic field, for the electric field, and then he got another one just like this for the magnetic field. And he, at that moment, knew exactly what light was, because that velocity turned out to be the velocity that he recognized as light. So he knew what light was. And what is light? Well, it turns out you can think of light like this. Let's imagine this is a three-dimensional drawing. It's actually a two-dimensional representation of a three-dimensional drawing. So what I'm going to do is I'm going to imagine an electric field that's sinusoidal. So this is there, and this is what I would call vertically polarized light, because the electric field is actually oscillating vertically. And then perpendicular to that is a magnetic field like this, and the velocity is in fact this, which equals c times, let's say, the hat vector of E cross B. In other words, if you take the cross product of E and B in that order, and you divide it by its magnitude, then you'll get a unit vector, and that unit vector points in the direction of the velocity, and its magnitude, of course, for this vector is going to be c, because I got c times that. So that's what light was as of Maxwell's discovery, which, by the way, we had just finished, all this time working with Huygens, where he said light was, in fact, a wave, and now this is confirmation of that. Now, if you went back a couple hundred years, and you'd say, oh, well, Newton had worked of light as if it were a series of particles, and he got the same equations, but that really didn't matter too much. It wouldn't be for another 30 or 40 years before everybody realized, oh, wait a second, there's something we got to work on, because these two things are seemingly contradictory. But that's what it is. And all of the radiation that's made up of this stuff, an electric field oscillating in one plane, a magnetic field oscillating in the other plane, such that E cross B is the direction of the velocity, all of that is what we call electromagnetic radiation. And I'm going to tell you the parts of it are great excess, undermines various industries, Marxism rules. And I'm going to go a little further and tell you that this is not this is not Roy G. Biv. This is Vib Gior. Okay, which hopefully you can tell, because obviously R should be next to infrared and V should be next to ultraviolet. But the big thing here is this side is about 750 nanometers, and this side is about 400 nanometers. So you can tell that that visible part of the spectrum is really, 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 really teeny. Okay. Now, one of the solutions of a wave equation is something like this. You could say E is equal to some E0 times cosine kx minus omega t. And then you'd have some kind of vector, which I'll call lowercase e hat, which in this case would be like, say, the y-axis. And then B would equal B0 cosine kx minus omega t. And let's say that one would be in lowercase b hat. And specifically, there exists something called the Poynting vector, Poynting vector. And that Poynting vector is S, and it's 1 over mu 0 times E cross B. Now, Oliver Heaviside invented this about the same time as Poynting did, but Poynting beat him to the actual publication, so it's called the Poynting vector. But the main thing is it is actually the energy per unit area. So it has units like of watts per square meter or something along those lines for this quantity. And that's what you do. Like if you want to calculate, hey, how much energy is being delivered over a square meter of the top of our atmosphere? Well, that would mean the S of the sun, the S for the sunlight on average is about 1,350 watts per square meter. Okay. So that's like the figure you'd use if you want to actually calculate how much square footage of solar panels would we need to supply the entire electricity requirements for the U.S. And people have argued, oh, you'd have to cover up half the continental U.S. with solar panels. No, you don't have to. In fact, you don't even have to cover up like Rhode Island. It's not even that big. I will tell you that 1,350 is, if I remember correctly, that should be roughly the flux at the upper atmosphere. By the time it gets to the surface of the Earth, it's a little bit less. And I'll also tell you that solar panels are only about 10% efficient. One last thing I want to say about this kx minus omega t. These things are called plane waves. And what that means is basically you can define a plane over which the electric field has a certain strength period. So you can imagine like the crest of one wave being an infinitely long line to the right, and basically everything along that line has a crest of an electric field. If you want to understand what this means, though, you can think of this kx minus omega t as a specific value. For instance, if kx minus omega t was, let's say, 2 pi, then you'd know E is equal to just plain E0 because the cosine of 2 pi is 1, right? So what I want to show you is that this wave, kx minus omega t, is propagating in the positive direction. So I'll say prop in positive direction, and kx plus omega t is in the negative direction. The way we can do that is say, let kx minus omega t equal, let's just say some angle phi. Solve for x. So what we're going to get is x is equal to, we're going to have omega over k times t minus, actually, when I put that, it'll be, yeah. So it'll be plus phi over k. So you see, t equals 0 implies x is equal to 0. T greater than 0 implies x is greater than 0. And T1 greater than T, or T2 greater than T1 implies x of T2 is greater than x of T1. So what we're saying is, as time goes forward, clearly this point on the wave that was corresponding to, say, a value of 2 pi is moving to the right. So that's what that is. If you had the same thing, kx plus omega t, and you set that equal to, let's say, this number, then you'd see x is equal to, in this case, we'd say negative omega over k times t plus phi over k. And you see it's moving in the negative direction. And can anybody look at this and tell from these two equations right here, can anybody tell me what the velocity of this wave is? Remember, it's like an equation, x equals x0 plus vt. So maybe comparing x equals v0, x equals x0 plus vt to that expression for x might help you. Anybody see it? How about this, omega over k? And I will tell you, omega is 2 pi times f, and f is 1 over t. So omega is equal to 2 pi over the period. And k is defined to be 2 pi over the wavelength. So if I put these in, I get 2 pi over the period over 2 pi over the wavelength, which equals wavelength over period, which equals wavelength times frequency. So this is the baby wave equation. And that's the one that you're going to use to figure out the wavelength, for instance, of 8:50 a.m. So what, and this will be the last part, what is wavelength of 8:50 a.m. and what is the wavelength of 93.7 FM? the key to doing that, I'm not going to calculate it, but the key to doing that is F is equal to 850 times 10 to the third hertz. And F is equal to 93.7 times 10 to the 6th hertz. V is equal to C, and V is equal to C, and that's it. Okay. So that's basically just about everything I'm going to ask you to be able to calculate. You're going to have to be able to calculate a pointing vector, at least its magnitude, know what it means, calculate wavelength if I give you a frequency and a speed, or if it's a particular radio wave, then or a particular EM wave, then you know the speed already. So all I have to do is give you the wavelength or the frequency, and you can give me the other one. So that's essentially all that you have to really be able to know. And then, of course, looking at these functions for the solutions to the wave equations. I'll cover more of this on Thursday, but you guys are free to go. And I'll wait for the last person to leave in case anybody has any questions.
Have a great day.
You too. Thank you, Haley. All right, that looks like it. It looks like everybody's gone. Bye, everybody. Have a good one.